how this signaling facilitates sexual reproduction and also contributes to reproductive isolation. Specifically, I'm interested in reproductive signaling between the male and female gametes. Now, most of this work has been done in external fertilizers like sea urchins, but a lot less is known about how this mechanism works in internal fertilizers such as angiosperms. So gamete interactions are important because they may have roles in procreative fertilization, or have roles in sexual selection or sexual conflict in the form of female choice or sperm competition in the female reproductive tracts across many organisms. And again, they might have roles in the evolution of reproductive isolation, but once again, most of this work has been done in external fertilizers. So today, I'm going to focus on the genetics and evolution of gametic interactions. And I'm doing this in an internal fertilizer, the wild tomato clade. So in this clade, we have around 13 described species that are around 2 million years diverged. They have a variety of their reproductive displays, and they also have lots of ecological diversity throughout their natural range in Latin America. So I'm focusing on three main parts. First, describing the male-female gamete chemoattraction within species, looking at the divergence in the signaling between species, and then a sneak review of the molecular mechanism. So in order to focus on the interactions between the gametes, I had to develop an in vitro assay, but to do that, I kept what happens in vivo in mind. So the pollen, as we know, grows down the style, the female reproductive tract, enters the ovary, and at this stage, this is when ovule guidance takes over. So the ovule secretes some sort of signal from its micropyle here that guides the pollen tube towards the micropyle and then allows it to enter and fertilize. So keeping this in mind, I designed an in vitro assay, and what I do is first pollinate a style, excise that style, place it onto a growth media along with excised ovules, and then around 10 to 15 hours later, depending on the species, the pollen tubes emerge from the cut end of the style, grow onto the growth media, and then I score these assays from the ovule perspective. So here, in this circle right here, we have a zone of attraction coming from the micropyle. So within this zone, if a pollen tube grows randomly on the plate within this zone and the pollen tube makes a dramatic turn, which is more than 20 degrees or more, towards the micropyle and makes contact with the ovule, this is evidence of targeting or evidence of chemoattraction. If, however, the pollen tube grows within the zone and just keeps on going, makes no angle changes, this is evidence of no targeting, no chemoattraction. So within species, I'm focusing on three main species. So we have Lycopersicon, which is the domesticated tomato, Pimpinellifolium, which is the closest wild relative, and Pinellii, which is the most distant wild relative in this clade. And for these assays, the pollen and ovules are from the same species. This is kind of what it looks like. So here's a short video of this happening. So this structure here is the style, the cut end is right here. These are all trichomes, so you can just ignore that. Here are three excised ovules, and a spoiler alert is that this ovule right here will be the one targeted. Okay, so the pollen tubes grow randomly out of the cut end of the style, and then here's the one we'll pay attention to. So it grows along the growth media, and then right about here, comes within the zone of attraction, makes an angle change, and makes contact with the ovule. So in case you can't see that, here is an outline of where the pollen tube grows, and the three zones of attraction for each of these ovules, once again coming from the micropyle, not the entire ovule itself. So focusing in on this one, you can see that we have a major angle change, and then several smaller angle changes towards the that micropyle in the sense that the pollen tube is following a diffusion gradient of that chemoattractant. We also see this minor angle changes in other species, as though, and so this is evidence that an ovule-derived chemoattractant is present. So if we replicate this, here we have proportion of ovules targeted from 0 to 1. Here we have the pollen species and the ovule species. So again, for conspecific assays, pollen and ovule come from the same species. And for this kind of in vitro assay, between about 50 and 80% targeting is considered average for this kind of assay. So for these three species, we do see some variation, but all of them lie within this range. So this is evidence there is an ovule-derived chemoattractant that causes or allows the pollen to locate the ovule for fertilization. So between species, again, I'm focusing on the same three species pairs, but the ovules and pollen come from different species. So this is, once again, what we have in conspecific assays. So first, focusing on Lycopersicon ovules, here with the two other pollen parents. So we have no reduction in chemoattraction for these pairs. So these two interactions, again, some variation, there's no reduction in chemoattraction. Moving on to the pimpinellifolium ovules, here for Lycopersicon, it's the closest relative. We have, again, no reduction in chemoattraction, but with Pinellii pollen, it seems the Pinellii pollen is not as attracted to this ovule signal. So we see a reduction in targeting and potentially species specificity of this chemoattractant. And also for Pinellii ovules, so this is the most distant relative, for both of the other species, we see a severe reduction and a significant reduction in chemoattraction between these two gametes. This is kind of what it looks like. So here we have a zone of attraction. The pollen tube comes within this zone and just keeps flying on by looking for another ovule that it's compatible with. So what is the relevance of this reduced chemoattraction in nature? So we see that these two wild species are genetically divergent in this clade, but their ranges overlap, so they're entirely sympatric, meaning that their gametes can come together in nature, and that this lack of, or this reduction in chemoattraction may be a source of reproductive isolation in these species. I'm going to continue looking at this interaction across other species pairs in this clade to continue to look at these patterns. So we see that we have ovule-derived chemoattractants. We see some divergence in the signals across species. So what is the molecular mechanism? So to figure out what this is, we had two main criteria. So the first is that among dicots, namely Trinia and Arabidopsis, the known chemoattractants are all CRPs, or cysteine-rich peptides. So we hypothesized that in wild tomatoes, this would also be a CRP. Second, chemoattractants have ovule-specific expressions, so specifically from mature but unfertilized ovules, as opposed to other maternal tissues. So if we look at RNA-seq data, in both pimpinellifolium ovules and Lycopersicon ovules, we have two really high candidates that are expressed really highly in these mature unfertilized ovules as opposed to other maternal tissues. So we took a look at these candidates, and structurally they are both actually CRPs. And so here we have the three species I talked about today in an outgroup. So Lycopersicon and pimpinellifolium have identical sequences for both of the candidates. But in Pinellii, the more distant relative, we see some pretty obvious amino acid changes. And so for both of these candidates, both fit our criteria, and so I'm going to follow up on both of these using functional assays in the future. Okay. So we do see this male-female gamete attraction, so I conclude that gamete recognition is a general mechanism across this plasmid plane. We see divergence in gamete attraction between species in some species pairs, but once again, I'm going to be following up on other species to look at these patterns more. And for the molecular mechanism, we have two strong candidates, but I have to follow up on them. And with that, I would just like to thank the Moyle